In cybersecurity, we're putting a whole lot of trust in AI to be our digital watchdog. But there's a pretty dangerous flaw in that trust. A lot of these AI models, they absolutely ace their exams in the lab, but then they completely fail when they face new threats out in the wild. People are calling this the AI credibility crisis. So today, we're going to dig into a really fascinating solution, a new method that teaches AI to stop just memorizing attack patterns and start truly understanding the meaning behind them. Okay, this chart right here really lays out the problem perfectly. On the left, you've got the easy split, and the AI models are scoring above 90%. You can think of this like an open book test, right? They've basically seen the answers before. But then on the right, you have the challenging split. This is meant to mimic the real world with new evolving threats. And just look at that drop. Accuracy completely plummets. It's a huge failure, and that's the absolute core of this credibility crisis we're talking about. So why on earth does this happen? Well, it's because of something called shortcut learning. Instead of actually grasping the concept of, say, an SQL injection, the AI takes a shortcut. It just learns that any piece of code with the text or 1 equals 1 is bad, and that works until an attacker changes it just a little bit. Then, all of a sudden, the AI is totally blind. It's kind of like the difference between actually understanding grammar and just memorizing a few phrases to get by. So, how do we fix this? Well, researchers have come up with a really clever new framework called SAM. First, we're going to dig into this whole AI generalization problem. Then, we'll explore SAM's super smart two-stage approach for handling descriptions and payloads. And finally, we'll get to see the results, which are pretty cool. All right, first up, AI generalization. Why do these models fall apart out in the wild? See, the thing is, real-world cyber defense isn't just about matching patterns we already know. It's about reasoning through brand new, unpredictable threats, those 0 days that nobody has ever seen before. The researchers who wrote this paper, they put it perfectly. The entire field has been kind of stuck on this problem for a while. You get these amazing results in the lab, and it creates this false sense of security. But then, those exact same models just break down the second they face a live network. And that creates this massive, really dangerous gap between what we think the AI can do and what it actually does. So how do we bridge that gap? Well, that brings us to the solution they're proposing, SAM, which stands for Semantically Aligned Language Models. The name itself is a huge clue here. The goal is to stop teaching the AI to just look at raw attack code and instead start teaching it the semantic meaning behind that code, using our own human language as the guide. At its core, SAM uses this really clever two-step process. First, in stage 1, it reads thousands of vulnerability reports written by human experts to build this detailed, organized map of all known cyber threats. Then, in stage 2, it trains a totally new AI to take a piece of raw attack code, a payload, and figure out its exact location on that map. This is how it transfers that deep semantic understanding from human text directly over to raw code. Okay, let's break down stage 1. I want you to think of this stage like we're training a master librarian. The AI's only job is to take thousands of unstructured, messy vulnerability reports and organize them into this perfect semantic library, where all the similar threats are grouped together, nice and neat. The technique behind all this is called contrastive learning, and honestly, it's way more intuitive than it sounds. You basically teach the model by showing it 3 examples at a time: an anchor description, a positive one that's similar, and a negative one that's different. The AI's only job is to learn how to pull that anchor and the positive example closer together on its internal map while pushing the negative example far, far away. This diagram shows us exactly how stage 1 works. So here's our triplet. The anchor is a description of an SQL injection. The positive example is another, slightly different description of that very same attack. And the negative example is a description of a totally different kind of threat, a directory traversal. All 3 of these get fed into the text encoder. The model's whole goal is to just keep adjusting itself so that in this representation space, the 2 SQL injection descriptions end up right next to each other, while that directory traversal description gets pushed way, way out. You do this millions of times, and the AI builds this incredibly robust semantic map of all the threat concepts. Okay, so with our library all meticulously organized by our master librarian AI, we're ready for stage 2. Now we introduce a new AI. Let's call it the expert student. Its one and only job is to learn how to take raw, messy attack code, the payloads, and correctly file them inside the library that our first AI already built. This process is called cross-modal alignment, and it's really the heart of the entire solution. We're aligning 2 totally different modes of data, human text and machine code. And here's the most critical part. The knowledge of our first AI, the librarian, is completely frozen. It becomes this perfect, unwavering teacher. The new payload model, the student, then has just one goal. Learn to place a raw TAC payload in the exact same spot on the map as its official text description. And this diagram shows that teacher-student dynamic just perfectly. You'll notice the top encoder for text is now labeled frozen. That's our teacher, and it's providing the correct answer every time. The bottom encoder, the one that processes the raw payload, that's the student. It's the only part that's still learning. The entire training process is now just about one thing, minimizing the distance between where the student thinks the payload should go and the teacher's fixed location. By doing this, the payload model is forced to inherit all that deep semantic understanding that was originally learned just from human text. So the big question is, after all this complex two-stage training, did it actually work? Did the AI's internal map of threats get any more organized? Well, let's take a look at the visualizations the researchers gave us. And wow, the results are, you can just see it. It's visually stunning. On the left, you're looking at the AI's understanding of all those threat descriptions before any training. Each dot is a threat, and it's a total mess, right? A complete jumble. Now look at the right. This is the same data after stage 1. The whole space has been transformed. You can see these clear, distinct colored clusters have formed. Each color represents a different category of threat. Our master librarian has successfully organized the library. And this right here, this is the final crucial result. This visualizes the raw attack payloads, which are represented by those stars. On the left, before stage 2, all the payloads are just one giant, unstructured black blob. The AI has absolutely no idea how to sort them. But now, look to the right. This is after the alignment in stage 2. Those stars, the raw attack payloads, have snapped perfectly into place, all organized within the colored clusters that were defined purely by text. This is the visual proof we were looking for. The deep semantic meaning was successfully transferred from human language to raw code. This beautiful visual organization isn't just for show either. It translates directly into performance. On that really challenging real-world test we saw at the very beginning, SAM achieved an accuracy of 68.1%. And that is a major leap over methods that are just relying on shortcut learning. And when you stack it up against other methods, well, SAM is the clear winner. It outperforms a standard fine-tuning approach by almost 6%, and it's nearly 20% better than a simple similarity search. This is the hard data, the quantitative proof that building that semantic map first gives you a real, measurable advantage against new and unseen threats. So, what's the big takeaway from all this? We started with the problem. Cybersecurity AI fails in the real world because of shortcut learning. The solution, SAM, attacks this with a two-stage process. Stage 1 is our librarian, using contrastive learning to organize text descriptions. Stage 2 is the student, using modal alignment to map raw attack code onto that library. The result is a much more robust AI, one that can generalize to new threats because its understanding is grounded not in superficial patterns, but in deep semantic meaning. Ultimately, this whole thing represents a fundamental shift in our thinking. It's about moving AI away from being just a simple reactive pattern matcher and moving it towards being an agent that can actually reason about the nature of a threat. This opens up some pretty incredible possibilities, which leaves us with a final question to ponder. If we can teach an AI to truly read and understand and attack today, how long is it until that same AI can learn to predict the next one?